In the
This
previous
conference will
class,
now be recorded.
we were discussing the things related to the I2C protocol. So we were actually into the program where our microcontroller, the PIC16F877A, had to communicate with the RTC. So RTC was DS1307. So the two chips which are on the same board had to be communicating with each other, and hence we had to go with the intra-board protocol, which was I2C protocol. So we saw how I2C has been working, the way how the communication happens using the I2C protocol, and also we saw the functions, how to configure the I2C in the microcontroller, how to make use of that I2C. Am I not audible? Am I not audible? Okay, so Aniket, he must have to be checking his internet. Okay. So we saw how to configure the I2C in our in our microcontroller. Then RTC by default it communicates with the I2C protocol. So you just have to like whenever you have to read from the RTC or write into the RTC, you have to go with the specific registers and you can write into that address. So address of the registers were given. You could write into that registers or read from the given address. So we discussed that so far. So since the past 3 days, we have been discussing the same protocol, which is I2C. So today I'm going to start with the last topic of the module, which is nothing but the CAN protocol. So this is the very last protocol we are going to discuss in this module, and actually the very last topic we are going to discuss in this module. So let us start with the CAN protocol in today's class. So if I have to start with, as I said, this is the last topic we are going to be discussing about, and the CAN protocol stands for Controller Area Network, and this protocol is basically by the Robert Bosch. So they had a need of network which was highly reliable, and it must have to be very simple. So they actually worked really hard and introduced the CAN protocol. So if you actually Google the story of the scan protocol, it generally talks about the car. Okay, so let me show you that. Okay, so it is something like this. So if you generally like Google a story about the CAN protocol, so it usually talks about a car. Okay, so they say the car has a lot of things. For example, there can be some steering. There definitely will be a steering for sure. So there will be steering. There will be some windows. There will be brake system. So they usually compare the car to a human body. So as we have things in our human body, there are several things which a car is being made of. So in our body there will be so many nerves going inside, so they will be connecting one part with the other. In the car also, there will be devices which had to be connected one with the other. But this car had actually multiple components. As I said, there's steering, there's wheels to be managed, there's accelerator to be managed. Multiple things have to be done in the car. So to connect multiple devices, even there was the connection happening. Okay, but they felt at some times they want one chip to be communicating with the other here. Okay, inside the car, they like when the automation came into picture, so whenever the car has to be designed, they wanted the systems to be communicating with each other, different systems to be communicating with each other. So that is when they wanted a reliable and a simple protocol, so they invented a CAN protocol. So maybe because sometimes some of the components might have to talk to each other, there had to be a network which is not complex, so it has to be simple and it has to be highly reliable. So that is why they worked hard and introduced the CAN protocol, which is nothing but the control area network protocol. So they minimized all things and formed a simple network, which is nothing but the CAN. So CAN is just not used in the automatic automation field. So these days it has been used in avionic fields as well. They have been used in commercial applications like the designing of lifts and all. So it has basically been used in many of the fields right now. And remember, it is completely a inter-board protocol. Okay, now let's see what and all we are going to see here. So first, to start with, I'll be going with the introduction to the CAN protocol. Then we will go with some basic concepts, whatever are being required. Then we'll understand how message has been transferred between the two chips, and then how is the error being handled. So in the message transfer, you will also see some of the frames, some different frames actually, and then you will see how to handle the error, and the last will be fault confinement. Okay, so these are the things we are going to discuss with respect to the CAN protocol. Guys, please pay attention. This is something which is really important. So for example, this is a protocol, as I said, is from the Robert Bosch. And if you people are like maybe applying placements to the Robert Bosch, this really helps. So it is because this is the area where the Bosch people are majorly concentrated on. Okay, so you have to be understanding how things happens with the CAN protocol. Okay, so let us start with the introduction first. The introduction of the CAN protocol says it is an asynchronous protocol. So what does asynchronous mean? What does asynchronous mean? Yes, so remember, there is no clock line present. Communication is happening without the presence of the clock. So clock line is not being there, and the two chips can communicate with each other. So that is the first feature of the CAN protocol. We have already discussed one more asynchronous protocol. Do you people remember which is that? We have discussed one more asynchronous protocol where the clock line is not being present when the communication has been happening. Yes, UART. So apart from UART, CAN is another protocol which is an asynchronous protocol. Then the next feature is it is half duplex. So remember, because of the half duplex, how many data lines will be present? Because of the half duplex, how many data lines? Yes, so the one which we saw, SPI, is all sorry, the I2C is also half duplex. So there is only one line present, one data line present. So half duplex in the sense two-way communication will happen, but there is only one party communicating at a given time. So half duplexes, it is having only one data line. Then coming to the next feature, it is multi-master, multi-slave protocol. Okay, so this protocol is multi-master, multi-slave protocol. So here we can refer the components as master and slave, but still we don't prefer referring it as master and slave. We usually refer the components or the devices of this protocol as nodes. Okay, so we don't refer it as master and slave. We usually refer it as the nodes here. Okay, in this protocol we refer it as nodes. So in UART we used to say it as host and the device. In SPI and I2C protocol we could refer it as master and slave only. But coming to the CAN protocol, it is multi-master, multi-slave, but the devices are referred as host. Okay, next. So this slide is talking about some of the basic concepts. Let's start with the very first thing, which is the example. Okay, so this is the example of a CAN protocol. Okay, as I said here, all the devices whichever are being present in the network are referred as nodes. So let's say this is node 1, this is node 2, this is node n. Okay, so all of them are being referred as nodes. So every device in the node, if you can notice, there can be n number of nodes in the network. So it is up to the configuration. So there can be n number of nodes. And if you can notice, every node is having three components for sure. One is a controller, The other one is a CAN controller. The third one is the CAN transceiver. Okay. So every node in the CAN network is going to have these three components. One is the controller, second one is the CAN controller, third one is the CAN transceiver. And one more thing you have to remember in case of CAN transceiver is one side of this CAN transceiver is analog, the other side is been digital. Okay, so this has been analog. This side of the CAN transceiver is analog. So the input what CAN transceiver takes is analog in this side, and the output it might give is the digital. Okay, similarly, if it is the ulta, it takes digital here, it gives out analog here. Okay, so it is like a converter in between. So the thing is, it takes analog thing. One side of the transceiver is analog, the other side of the CAN transceiver is the receiver. So as you can see, in some of the nodes, okay, there can be controller and CAN controller built in. So that is why we have done a grouping here. In some of the devices, there can be controller and CAN controller built in. Okay, for example, our microcontroller, the PIC16F877A has got the controller and CAN controller built in, but CAN transceiver has to be added externally. If the communication has to be done using CAN protocol, you have to add the CAN transceiver separately. But later, as of now, we don't have any such devices which has got all the three of this built in. But later, tomorrow, in future, there are chances of getting a node which is having all of these three devices built in. So it can have a controller, it can have a CAN controller, it can have a CAN transceiver built in at times, maybe going ahead in future. As of now, we don't have such devices, but there are chances where a node can be developed with built-in controller, built-in CAN controller, and built-in CAN transceiver also. Okay, so this is just an example of the CAN protocol. Okay, so all the devices in the network are typically being referred as nodes, and it has got three things. Every node in the network should have got three things: controller, CAN controller, and CAN transceiver. So some of the components can be built in and some of the components can be externally added or need to be externally added. So these are the examples of CAN protocol. Then going ahead, uh, after the examples we have got is the version of the CAN protocol. If you can see, the very first column gives you the nomenclature. The second one gives the ISO standard. Third one is the maximum signaling rate, and fourth one is the identifier. So we have got three types of CAN protocol. Okay, so one is with a low speed CAN, which is having this ISO standard. The signaling rate is 125 kbps and the identifier is of 11 bits. Okay, then there is CAN 2.0A with the ISO standard given this, which is having 1 Mbps of signaling rate and the identifier is also again of 11 bits. Then CAN 2.0B, the standardization is this: maximum signaling rate is 1 Mbps and the identifier is 29 bits. Okay. So what happens in this case? Like, how is the communication happening? So you have to understand that. So generally in case of I2C protocol, assume there are multiple nodes in the network. So just like the I2C protocol, in this case also, let's say there are multiple devices in the network. As you did in the I2C protocol, first thing, what was that? What was the first thing you used to do in the I2C protocol? Come on, what was the first thing you get to do in the I2C protocol? When the communication has to be started, what is the first thing you do in the I2C protocol? Yes, so you have to check if the bus is been idle or not. So similar to the I2C protocol, here also the bus will be the nodes will check if the bus has been idle or not. Whenever a communication has to be started, it checks if the bus has been idle or not. So only if the bus has been idle, communication can be initiated. So first of all, any node who wants to communicate in the network will check if the bus has been idle or not. So assume right now if the bus has been idle. The next thing what happens in the CAN protocol is, so usually in the I2C protocol, you had to go with the start bit. Okay, so to check if the devices have been awake or just to create an awareness, you had to start with the start bit. So here usually what happens is whoever wants to start the communication, definitely the first thing he or she does is to check if the bus has been idle or not. Later when he finds out that the bus has been idle, he directly starts transmitting the message. Okay. So people means the nodes, whoever have been in the CAN network, so they directly start transmitting the message. Once the bus has been idle, they directly start transmitting the message. Now, if the message has been transmitted, okay, how many of the nodes do you think will receive that message? How many nodes do you think will receive the message if they directly transmit the message? Come on, how many nodes in the network? Yes, whichever nodes have been connected in the network, all of them will receive the message. Okay, remember, whatever nodes have been connected in the network, whichever devices have been active in the network, all of them will receive the message. Okay, now let's say I have sent it to some specific node, and only that specific node has to take the action. But whatever I have transmitted as a message, everybody can see it. Now, how to identify which is the node which has to take the action? So, how to tell that this one is the node for which I have transmitted the message? So, that is judged by looking into the identifier. Okay, so every message when it is being transmitted will have a identifier transmitted along. Okay, and whoever's identifier gets matched, based on that the action will be taken. So let's say node 1 wants to communicate with node 3. He's going to check the bus idle condition, he directly transmits the message. And everybody in the network will look into the message, and what do they specifically see? They look into the identifier. So if the identifier is a match, he can look into that message and continue working on it. Or if the identifier is not a match, they'll ignore. Whoever node gets the matching identifier in that message will take the action and transmit, means will continue to communicate. Okay, so previously in case of I2C protocol, it was software addressable. Every device had a unique address given to it, which was software addressable. Here we don't have an address as such. So it is called as an identifier. Depending on the identifier, the specific node has to take the action. Now, the question is, what is an identifier? Okay, so the question right now is, what is an identifier? Now, to make you understand what is an identifier, let me give you some non-technical example. Okay, so let's say I am in this virtual class. So right now we are actually in this virtual class. So I do have around some 30 plus participants. Okay, as of now I've got some 30 plus participants. Let's say I transmit a message saying that something like this: all boys work on assignment 1. Okay, so I say something like this: all boys work on assignment 1. Now looking into this message, can you tell me what is the identifier? What is the identifier here? Yes, it is the boys. The identifier here is the boys. So what actually happens is, initially, so I transmit the message saying all boys work on assignment 1. Now do you think girls will start working on assignment 1? Is there any chance of girls starting working on assignment 1? No, definitely not. But I say boys. Now tell me, if I say all boys start working on assignment 1, how many of you will start working? How many of you will start working? Don't you think every boy in the group will start working on assignment 1? Yes, all the boys in the network will start working on assignment 1. So this is an identifier. Similar to this, if I have to tell you, let's say I'm transmitting a message in the node. Okay, assume I'm transmitting a message in the node and all of them will receive the same message. Okay, and there are chances where multiple nodes can accept the message and start working on it. Okay, so like a broadcast, not to everybody, but there can be multiple devices who can be commonly addressed in the network, and there can be multiple devices whose identifier is been matching, and multiple devices can start working at the same time. Okay, so that is how the CAN protocol is going to work. So there are possibilities. In this case, all the boys might start working on assignment 1. So same way in our network also, we have got multiple nodes, and whichever node matches with the message or the identifier is going to work on the given message. So this protocol is a multicast protocol. Okay, there are possibilities that multiple nodes accept the message and they will start working on this message. Okay, now as per our discussion, the protocol is asynchronous and it is half duplex. So if it is half duplex, you know there has to be a single line present for the sake of communication. But if you see the slide of this example, there are two lines. See, first of all, clock is not there. And I said data line should be only one. But here if you see there are two lines. Remember guys, both the two lines are corresponding to the data line only. Okay, so this is corresponding to the data line itself. Physically, if I have to tell you, these two are the lines of a data line. These two are the lines of data line, and they are in the form of twisted pair. Okay, so yes, I have got only one data line. Combining these two, it is considered as one data line only, and these two are formed using the concept of twisted pair cable. Okay, and this is the biggest advantage of the CAN protocol. Okay, so this one's the biggest advantage of the CAN protocol. Now for data transmission, I have to be using this twisted pair. So what is the advantage of this twisted pair is it allows noise cancellation. So that is the major advantage of this twisted pair. So less the noise is reflected, more the transmission will be good. So here also every transmission has got a termination, just like other terminations. CAN bus has also got a terminating resistor around 120 ohms on both the sides of the terminating resistor, and that has not been grounded. Okay, and the CAN protocol is working like NRZ, means non-return zero. Okay, we have got a twisted line. Let me be specific. We have got a twisted line. Your data line is a twisted pair cable. One of the line is called as CAN high, the other line is called as CAN low. Okay, so CAN high, CANH, and the other one is CANL. So it is CAN high and it is CAN low. Okay, and as I said, in case of transceiver, one part is analog, the other part, one side is analog, the other side is digital. So transceiver will convert the analog message to the digital. Now, let's say I have to transmit a message. So first I will check if the bus has been idle or not. If the bus has been idle as that of I2C, so communication is almost similar to that of I2C itself. So in I2C, if you remember, we could have checked the bus idle condition. If the bus is idle, what did we read at the SDL line? In the explanation, I said if the bus has been idle, what would be reading at the SDL line? Come on, in the explanation, I said what will be reading at the SDL line? Are you people there? What were we reading at the SDL line? We just discussed in the previous two classes. So I should have been reading a 1 if there is no communication happening. If the bus has been idle, I should have been reading a 1. If the bus has been busy, I should have been reading a 0. Okay. Now I'm telling there are two lines corresponding to a single data line. It has been splitted into a twisted wire cable as can high and can low. Now how to confirm it as a 0 or how to confirm it as a 1? Or let's say I want to transmit a 0 or I want to transmit a 1. How do I transmit 0 or 1 using two cables is the question. And also I said this transceiver, one side of it is the analog, this side is analog and this side is digital. So I am transmitting 0 or 1 in the analog form which will be converted to the digital by the transceiver. So let's say I want to transmit 0 sometime. Okay. Or let's say I want to transmit 1. So if I have to be transmitting a 1, remember both of the can high and can low has to be uh, carrying a bias voltage. Okay, bias voltage in the sense mid voltage. So if I have to transmit a 1, both can high and can low should be transmitting. Let's say my maximum voltage is 5 volt. Okay, assume the system voltage is 5 volt. So can high should be transmitting 2.5 volts and can low should also be transmitting 2.5 volts. Okay, but if it is 0, okay, let's say it is 0 I want to transmit. So can high has to be transmitting, sorry. So this is can high. Can high has to be transmitting 3.5 volts. Okay, so can high has to be transmitting 3.5 volts and can low has to be transmitting to 1.5 volt. So that is how you will say whenever you have to be transmitting a 0 or a 1. If you have to transmit a 1, you have to be passing can high with 2.5 and can low with 2.5. If it is a 0, it has to be uh, can high with 3.5 and can low with 1.5. Let me show you a simple example. So let's say I want to transmit the message something like, just an example. So let's say I want to transmit the message as 1010. Okay. So how the transmission will happen? This is voltage and this is time. Okay, so this is voltage and this is time. So let's say maximum here is 5 volt, minimum here is 0 volt. So in between is 2.5. Let's say this is around 3.5 and this is around 1.5. Okay, so I'm taking it like this. It is 0. This is 1.5. This is 2.5. This is 3.5. And this one's 5 volts. So let's say I want to transmit 1 initially. Okay. So if I have to be transmitting a 1, both can high and can low has to be having a 2.5 voltage transmitted. So this is how I transmit a 1. Okay, so this is 1. Let me write it down. This is 1. Okay. Then after this, let's say I want to transmit a 0. CAN high should be having 3.5 volts like this, and CAN low should be having 1.5 volts. Here is 1.5. I took pretty big graph. Okay, so that is how you are going to transmit a 0 here. So this is CAN high, which is carrying 3.5 volts. This is CAN low, which is carrying 1.5 volts. And this is how a 0 gets transmitted. Then let's say I want to transmit a 1 back. So something like this. Okay, so this is how you are transmitting a 1. Both CAN high and CAN low has to be carrying 2.5 volts, the bias voltage which is a mid-range. Again, if I have to be transmitting a 0, CAN high has to carry 3.5 volts and CAN low has to be carrying 1.5 volts. So this is how uh, data will be transmitted in a serial manner using the CAN protocol. Further, if you want to transmit a 0, you can extend this. Else, if you want to transmit a 1, you have to be transmitting 2.5 volts in both the high and the low wires. Understood how data transmission happens in CAN protocol using two wires. So both of them are considered as a single wire. It is a twisted cable which is contributing for a single data line in the CAN protocol. Understood how 0 or 1 gets transmitted physically using the two cables? Everybody? Okay. So we saw the examples, we saw the versions. So as said earlier, there is an absence of node addressing, means it is not software addressable. So message will have a message identifier, and depending on that, the action will be taken. So based on the identifier, it is getting accepted. And remember, this is a multi-master, multi-slave protocol. And if multiple masters start communicating at the same time, who is going to win the bus is a question. Okay, so who is going to win the bus is a question. So according to the information, remember, the message having the lowest identifier is going to win the bus. Whichever message is having the lowest identifier is going to win the bus. Means that one is the one who is going to have the highest priority. And there is a non-destructive arbitration system by CMA for the collision detection. So arbitration system is by carrier sense multiple access protocol, and this is separate. Okay, and the simple transmission medium is there. Okay, there's a simple transmission medium. As I said, there's twisted pair with CAN high and CAN low. Okay, next, let's go to the properties. Okay, so to talk about the properties of the CAN protocol, first of all, so let's see the properties of the CAN protocol. I understand it is too much of theory, but it is really important. So first priority says it is the prioritization of the messages. So here, as I said in the previous slide, lowest identifier is going to win the bus. Okay, especially when multi-master communication is happening. That is, let's say two nodes are transmitting at the same time. Whoever is having the lowest identifier will get the highest priority. So the one with the lowest identifier is going to win the bus. Okay, so prioritization of the message happens that way. Then there is a guarantee of latency times. Okay, this means the time taken to transmit from one point to another point is guaranteed. Okay, so it is having the same data rate. So wherever you need to transmit, the transmission is happening in a guaranteed rate. So it has already been tested and it will always be same for sure. And the next property says The configuration is flexible, means anytime I can add a new node and anytime I can remove an existing node. So that flexibility is there. So we have that flexibility. You can add the node anytime, you can remove the node anytime. Then the next is multicast reception with time synchronization. So yes, multiple messages can be accepted by multiple nodes, and there is a system with wide data consistency as well. Okay, so you cannot suspect the quality here. An error is an error. So getting an error at times is very less. It is a multi-master protocol. It is multi-master as well as multi-slave. It comes with error detection and error signaling. So it can detect the error as well as it can signal the user about the error. Thing is, it cannot differentiate what the error is. It cannot identify the specific error, means it cannot tell this is the particular error, but it can just sense the error. Okay, so it is going to sense the error. An error is an error, whatever type of error it might be. An error is an error, and it has got the error signaling. So it can indicate that whenever an error is being detected, it can indicate us. Then another feature is automatic retransmission. Okay. So usually when you go with the I2C protocol, let's say two masters are communicating, and you people know that one of a master can only be communicating in a given time. Let's say one master is communicating and one master left the bus seeing that the other master is being communicating. So let's say I have transmitted the data, and because of the arbitration failure, I stepped out of the communication. In case of I2C, if you have to transmit the message again, you want to start the communication, everything has to be transmitted again manually. So if I have to start the communication, everything has to be transmitted manually again. But in case of CAN protocol, let's say I transmitted the message and then came out of the transmission because of data arbitration. So in that case, what happens is automatically the message, whatever I transmitted, will be transmitted by the protocol itself. So it is automatic retransmission. So it can retransmit the message by itself. You need not go to the network and try transmitting it. So once you have tried transmitting and you didn't get the chance of transmitting, so retransmission happens by itself automatically. You don't have to be saying it. Okay, and also distinction between temporary errors and permanent failures of the node is there. So it can identify what is the temporary error, what is the permanent error. So it can easily identify it. It can detect, and automatically, if it is a permanent error, the nodes will be switched off. Okay, so if it is a permanent error, the node will be actually removed from the network. So these are the properties of the CAN protocol. Clear? Is this been clear? Okay. So let's go with the next slide, which is talking about the layered architecture. Have you people heard of OSI model? Have you people heard of OSI model? There's something called as OSI model. Do you people remember the layers of OSI model? You tell me how many layers do you have in the OSI model? Yes, so OSI model has got 7 layers. So this slide is talking about open system interface. Yes, it has got 7 layers. So it is talking about the layered architecture. This protocol is again a layered protocol, and it is derived from OSI model. Okay. So OSI is a basic theoretical model, and lot of the protocols have been designed with the help of the same layered architecture. So I hope you remember the 7 layers of the model. So these are the 7 layers of the model. It has got application layer, presentation layer, session, transport, network, data link and the physical layer. So what happens is in the CAN protocol, we only have got three layers. So there is application layer, there's data link layer and the physical layer. Let us understand what and all happens in each of these layers. Okay. So first I'm talking about is the data link layer. That is the logic link which is having LLC. That is the logic link control. So it has the acceptance filtering, means whoever is going to accept the message, they have the acceptance filtering. So there is an overload notification, means if your data is overloaded and you are not getting time to accept the data, then it has a overload notification also. Then there is recovery management, means if you are going out of the bus, then this layer helps you in recovering the management. So then there is MAC, which is medium access control. So here data encapsulation, data decapsulation happens. Then there is something called as stuff rule, which needs to be followed when a frame coding has been done. So we will see what is this stuff rule. This is actually been followed by the CAN protocol. We will see it at the end. And this layer also detects the error. It does error signaling, and if needed, it sends the acknowledgement. So this layer is the one who sends the acknowledgement if there is any requirement. And serialization or deserialization of the messages also happens in this layer. So these are the duties of the data link layer. Coming to the physical layer, it does bit encoding and bit decoding. There's timing, there's synchronization. And coming to the application layer, it is nothing but your microcontroller. Okay, so these are the things what happens in the layered model of the CAN protocol. There's application, there's data link, there's physical layer. So application layer is your microcontroller, data link layer is your CAN controller, and physical layer is the CAN transceiver. Okay, so that is how the CAN protocol is being designed. So very basic thing up to this was just completely theoretical things. Here is an important and interesting topic which is associated to the CAN protocol. Okay, so this is much interested. This is the most interested topic out of the CAN protocol, because this is what we have to be concentrating on. At the end, what do we do is transmit the frame. Okay, we have to transmit the frame. So we have to know different formats of the frame and different types of the frame. Okay, so at the end we are going to transmit. I'm keep telling that I'm going to transmit the message. So what is that message? It is a frame. So I'm going to transmit a frame in the CAN protocol. So we have to understand the formats of the frame and the types of the frame. And if you see the frame format, there are two types of frame format. One is a standard frame, the other one is an extended frame. So one is a standard frame and the other one is an extended frame. How are you going to differentiate whether the frame you have got is a standard frame or a extended frame? Is looking into the identifiers. So if the frame has got 11 bits of identifiers, then it is called as a standard frame. And if the frame has got 29 bits of identifiers, it is called as extended frame. Okay, so we have got two types of frame formats. So to talk about the frames, we have got four types of frames: data frame, remote frame, error frame, overload frame. Okay. So when is the data frame transmitted? Whenever you want to transmit the data frame will be transmitted. Whenever you want to request the data, remote frame will be transmitted. Let's say you want to read, you want to request the data from another node. You're going to transmit a remote frame. So the node will look into the remote frame and understand somebody is expecting data from me, and it is going to transmit the data. So if you want to transmit the data, you transmit it using the data frame. And if you want to get the data from another node, you're going to transmit a remote frame. Then after that, there is an error frame. So whenever there is an error happening, so there has to be an error frame getting generated. And let's say between two devices, okay. So let's say between between the two frames, assume you are transmitting two data frames or you're transmitting two remote frames. And between the frames, you want some gap in between or you want some time in between. You're going to transmit a overload frame. Okay. So data frame is when you want to transmit the data. Remote frame is when you want to get the data from another node. Error frame is to indicate the error. Overload frame is to have a gap maintained between two data frames or between two remote frames. So if you understand data frame, remote frame is very similar to that. If you understand error frame, overload frame is very similar to that. Okay, so data frame and remote frame are similar to each other. Error frame and overload frame are also similar to each other. Okay, so now the task is to understand these four frames. It is really important for you to understand these four frames. So let's start with the very first frame, which is the data frame. So whenever you have to transmit the data, you are going to transmit a data frame. So what and all does this data frame have is a question. Okay. Remember, data frame consists of 7 fields. Data frame is consisted of 7 fields. So first one is the start of the frame. Second one is the arbitration field. Third one is the control field. Fourth one is the data field. Fifth one is the CRC field. Sixth one is the acknowledgement field. And seventh one is the end of the frame field. So let me take these things noted. So first one is the start of the frame. Let me note it down. Start of the frame. Then second one is the arbitration field. Then third one is the control field. Okay, so after control field, what we have got is the data field. And after data field, sorry, it is DA. Okay, so it is the data field. After data field, it is the CRC field, then acknowledgement field, and acknowledgement field. Okay, so after acknowledgement field, it is the end of the frame field. Okay, last one is the end of the frame. So let's write EOF, which stands for end of the frame field. Okay, so first one is the start field. This is the field which is used to initiate the start of the data frame. So SOF is the start of the frame field. So this is usually 1 bit. Generally start of the frame has been 1 bit. Then is the arbitration field. This is the field in which it is getting decided who is going to win the bus. Okay. So who is going to win the bus? I hope you know it is according to the identifier. Whoever is having the lowest identifier is going to win the bus. So arbitration field is the one with which we can conclude which node is going to win the bus. Then is the control field, data field, CRC field, acknowledgement field, and the end of the frame field. So this arbitration field can either be of 11 plus 1, 12 bits. Okay, so this can either be of 12 bits and or it can be of 11 plus 1 plus 1 plus 18 plus 1. So it can be of 32 bits. The arbitration field can either be of 11 bits or it can be of 32 bits. Then control field is generally of 6 bits. Okay, then data field is, it varies. It can be 0 to 8 bytes. Okay, data field can be of 0 to 8 bytes. Then we have got CRC field, which stands for actually cyclic redundancy field, cyclic redundancy check field, and this is of 6 bits again, not 6, I'm sorry, 16 bits. And then we have got acknowledgement field, and the last will be end of the frame. So this is actually 7 bits. So how much is the acknowledgement field? We will see it. Okay, so these are the 7 fields which you can see in the data frame. So first let us understand each of these fields, then we will get back to the frames. Okay, so then we'll get back to the data frame, the remote frame, the end of the frame, and sorry, error frame, and the overload frame. Okay, so we'll get back to the types of the frame. First let us understand the fields here. Okay, so I'm coming to the fields. So there's control field, arbitration field, data field, CRC field, and the ACK field. So first, before we start, we'll go according to what I have made a note here. So first is the start of the frame field. This is generally of 1 bit. Okay, so this is generally of 1 bit, which is a low bit. Okay, so low bit means it is 0. Okay, start of the frame is just 1 bit, which is 0. Okay, then the next field, let's go with the control. Okay, did I change the order here? Okay, first is arbitration and control. Okay, so let's go according to this itself. So first I'm going to discuss is the control field. Okay, now coming to the control field. So I said it is having 6 bits. Okay, let me go here. I'm talking about the control field which is having 6 bits. Okay, so which are those 6 bits? Let me tell you. The first bit is the IDE slash R1. R1. Then the next bit is R0. Then the next bit is DLC3, DLC2, DLC1, and DLC0. So these are the 6 bits of the control field. So there is IDE slash R1. So then there is R0, which is called as the reserve bit. R0 is the reserve bit, and this is DLC3 to DLC0. DLC stands for data length count. Okay, and it is of 4 bits. So using this, I will be telling how many bits of data I'm going to transmit. Okay, for example, let's say I'm transmitting 0 bytes of data. Let me copy it here itself. Okay, so let's say I'm going to transmit 0 bytes of data. I'm going to write 0, 0, 0, 0 like this. Just a minute. Like this. Okay, so if I'm going to transmit 0 bytes, then I'm going to have 0 written like this. Then let's say I'm going to transmit 1 byte of data. So it is 0, 0, 0, 1. So this is to indicate I'm going to transmit 1 byte of data. Like this, I can transmit data of 0 to 8 bytes. Okay, so if it is 8 bytes of data I'm going to transmit, I'm going to say it as 1, 0, 0, 0. So this is how I'm going to tell 8 bits of data, 8 bytes of data is what I'm going to transmit. So how much data we are going to transmit between 0 to 8 bytes? I'm going to say it by using the data length count bits, which is the 4 bits of the control field. Okay, so R0 here is reserved. The bit here is been reserved. Then after that, I have got another bit by the name IDE slash R1. Some of the times this is treated as IDE, some of the times it is treated as R1. So for now, let me keep it as a question mark. So when is the bit treated as IDE and when is the bit treated as R1? I'll keep it as a question mark. Okay. So next, after the control field, I'll go with the arbitration field. Okay. So let me talk about the arbitration field right now. So I'm talking about arbitration field. So remember, arbitration field is either of 11 bits, 11 plus 1, 12 bits, or it is of 32 bits. So the next field I'm talking about is the arbitration field. Okay. So initially, as per the data frame, the node who wants to start the communication will first check if the bus has been idle or not. Okay. So what type of protocol is this? Is this a synchronous protocol or an asynchronous protocol? Is this a synchronous protocol or an asynchronous protocol? Yes, this is an asynchronous protocol. Okay. Remember, this is an asynchronous protocol. That means there is no clock line. Okay. Because there is no clock line present in the communication, we have to trigger some signal in order to get the attention of the receiver. Okay. So we have to get a triggering signal sent in order to get the attention of the receiver. So what am I going to send initially is the start of the frame bit. Okay. So what will I do? I will transmit the start of the frame. So every node in the network is going to receive the start of the frame bit, and they will understand somebody is trying to communicate. Let me pay the attention. Now every node in the network is paying the attention. After receiving the start of the frame, what do you think the other nodes are expecting? What is the next thing the nodes will be expecting? Come on, after the start of the frame, what is the next thing nodes will be expecting? Guys, what were they expecting in case of I2C protocol? After the start bit, what were they expecting in I2C protocol? Come on, guys. Please answer. What were they expecting? What is the next thing I'm going to transfer or transmit if I have to start the communication? Yes, I used to pass the unique address. Do I have unique address in our case in case of CAN protocol? No, we don't have a unique address. So all of them, not data directly, it is the identifier. So all of the nodes in the network will be next expecting the 11 bits of identifier. So let me tell you, they are expecting identifier, okay, which is of 11 bits. So all the nodes in the network are expecting 11 bits of identifier. So once 11 bits of identifier is being received, the next bit all of them will be expecting is the RTR. Okay, all of them will be expecting the next bit as RTR, and RTR is nothing but the remote transmission request. Okay, so we saw in case of I2C protocol, we used to pass the unique address along with the intention, whether we want to read or we want to write. So in our CAN protocol, we have this RTR. So if we want to do the read operation, RTR will be a 0, and if you want to do the write operation, RTR will be a 1. Sorry, it is ulta. So if we want to do the read operation, RTR is 1, And if RTR is 0, it is the write operation. So let me write it here. 0 for read and 1 for write. Sorry, I'm saying it again ulta. So 1 for read and 0 for write. Okay, it is something like this. So first start of the frame, then identifier, then the intention, RTR. So RTR stands for remote transmission request. It will be 1 if I want to do the read operation. It will be 0 if I want to do the write operation. So after this, okay, after receiving the RTR, the next bit they are expecting is nothing but IDE. Okay, the next bit what the receiver is expecting, the node has been expecting is IDE. Now what is this IDE is? IDE stands for identifier extension flag. Okay, so it stands for identifier extension flag. So what happens is, based on this IDE, the nodes will decide whether it is the standard frame I'm going to receive or it is the extended frame I'm going to receive. So I hope you remember standard frame had 11 bits of identifier and extended frame has 29 bits of identifier. So how to tell whether it is the standard frame I'm going to receive or it is the extended frame I'm going to receive? It is depending on the IDE. So if this IDE is being 1, it is extended. Okay, if the IDE is been 1, it is extended frame. If the IDE is 0, it is the standard frame. Okay, 0 for standard and 1 for extended. Okay, so what happens after identifier? It is RTR, and after RTR it is IDE. So let's say right now IDE is been 0. Okay, so assume IDE is been 0 this time. So when IDE is been 0, remember it is the standard frame, and if IDE is been 1, it is the extended frame. So if it is the standard frame, as I said, 11 bits is the identifier, then 1 bit is the RTR, and after 11 bits are been received. Okay, so what is the next bit? It is going to receive the control frame, which is R0. Then it is going to receive the this DCL2, sorry, DLC3 to DLC0. Okay, so all of the nodes have, let's say ID is been 0, that means it is the standard frame. So because it is the standard frame, remember all the nodes have received the identifier, they know the intention. So directly they start with the control frame, which is R0, and then the length of the data which they have to be receiving. So they expect the control frame directly when IDE is been a 0. Okay, this is one scenario. So what is the other scenario? Let's say people means the nodes in the network has received the start of the frame. Then let's say they have received 11 bits identifier, RTR also, and IDE also. So let's say this time people have received IDE as 1, or let's say nodes have received IDE as 1. So IDE 1 in the sense it is an extended frame. If it is an extended frame, how much is the length of the identifier? If it is the extended frame, how much is the length of the identifier? Yes, it is 29. And out of, come on, why is that 32? It is 29. Out of the 29, okay, how much of the identifier we have already received? How much of the identifier we have already received? Quick. Yes, 11 bits are already received. How much is left? How much is left? Quick. How much is left? Yes. So 18 more are left. Okay. So what happens is when IDE is being seen as 1, the nodes will understand This time I am going to receive an extended frame. Okay, if it is extended frame, it is 29 bits of the identifier, and it will think I have already received 11 bits, I want 18 more bits. So it will tell, means next it will be expecting extended identifier. Okay, so it is expecting extended identifier which is of 18 bits. Now, this RTR, whatever it received, it is not treated as RTR. It will be treated as SRR. Okay, it will be treated as SRR. And SRR stands for Substitute Remote Request. Okay, so it is standing for Substitute Remote Request. So it receives 18 bits of extended identifier, and then later it is going to receive the actual RTR. Okay, it is then going to receive the actual RTR. Then after that it is R0, means the control frame. So it is going to receive it as R0, sorry, it is going to receive R1, one reserve bit, then R0, then everything of this. Okay, so something like this. So this is how the frame would look like if it is an extended frame. So first, if it is a normal frame, it is a standard frame, ID will be 0. So first it receives the start of the frame, then 11 bits of identifier, then intention. It finds out ID to be 0 in standard frame. I have already got 11 bits of identifier. So give me the rest. So R0 from the control frame and DLC3 to DLC0 from the control frame. So if it is the extended frame, first it receives the start of the bit, then 11 bits of identifier, then RTR, then it checks IDE whether it is 0 or 1. If it is 1, it realizes that I have to be receiving a extended frame. What I have received so far is only 11 bits of identifier. So the 1 bit I received was not the actual RTR. It was the substitute for the remote request. So what it receives next is the 18 bits of extended identifier. Then it receives actual RTR. Then R1, R0, DLC3 to DLC0. So if you can see, I don't know how to draw things here. I just had to underline. Okay. So anyways, let me tell. So in case of the standard frame, this much is the arbitration field. Okay. And this much is the control field. I don't know how to highlight it. Okay, I'll just use this pen. So this much is the arbitration field. Okay, 12 bits of arbitration. I said here. So if it is the standard frame, it is 12 bits of arbitration. If it is the extended frame, it is 32 bits of arbitration. So this is the standard frame. So it has got 12 bits of arbitration. Then this is the control field. This is the arbitration field. This is the control field. Arbitration field is of 12 bits. Control field, you can see it is IDE, then R0, DLC3 to DLC0. Then coming to the extended frame, so 11 bits of identifier, 1 bit of SRR, IDE, extended identifier, and RTR. Together forms 32 bits of arbitration field. Then from R1 to DLC0 is the control frame. And control field, I'm sorry. So this is the arbitration field, this is the control field. So in case of extended frame, ID is a part of the arbitration field. In case of standard frame, ID is a part of the control field. Understood why is that ID slash R1 in the control field? Understood why is it ID slash R1 in the control field? People, is this been clear? And understood 12 bits of arbitration field in the standard frame and 32 bits of arbitration field in the extended frame. Is it clear? Okay. So that is about our, so we discussed on start of the frame, we discussed on arbitration field and control field as well. So let's go with the next field, which is nothing but the data field. So you can see here the identifier of the standard format corresponds to the base ID in the extended format. So RTR bit is the remote transmission request and must be 0 in the data frame as of now because you are going to write. So SRR bit is the substitute remote request and is recessive, which is 1. Remember guys, recessive means 1, dominant means 0 from now onwards. Recessive bit means 1, dominant bit means 0. So initially the RTR will be 0 for the data frame. When will I use data frame? Whenever I want to transmit the data. Means the intention is to write. So I hope you remember, write is 0 for the RTR. So in the data frame, RTR will be 0. In the remote frame, whenever you want to read, it will be 1. Okay, reading will be 1. So SRR stands for substitute remote request and it will be 1 all the time. Okay, recessive means it will be 1. So ID field indicates whether the identifier is extended and should be recessive in the extended format. So if it is extended, ID will be 1. If it is standard frame, ID will be 0. So the extended format also contains 18 bits extended identifier. So that is about the arbitration field. Coming to the data field, it is simple. It will contain 0 to 8 bytes of data. It depends on what you have said in the control field. So here using this, you must have been telling how many bytes of data you're going to transmit. Depending on that, the data field will vary. So if it is 0 bytes you want to transmit 0 bytes here. If it is 1 byte, 2 byte, 3 byte, how much ever bytes of data you want to transmit, you can transmit using the data field. Okay, after that, it is the CRC field. So CRC field is the 16-bit field. Okay, so CRC here, cyclic redundancy check. So this bit is, this field is of 16 bits, which is further divided into CRC sequence and CRC delimiter. Okay, so CRC delimiter is a single recessive bit, means this is always 1. Okay, so CRC delimiter is a single recessive bit, this is always 1. Coming to the CRC sequence, it is the rest 15 bits. Now you have to know what is this 15 bits. Guys, tell me, in case of UART, to check if the data has been transmitted properly or not, how did we use to confirm? What was there to confirm if the data has been properly transmitted or not? Come on, remember it and tell me. Yes. So we had something called as the parity bit. There was a single bit which was used to find out whether the data has been transmitted properly or not. So this is very similar to that of parity bit. So usually what happens is in the CAN protocol, whenever you are transmitting the data using some polynomial method, the protocol calculates the CRC sequence, which is of 15 bits. Okay, so you don't have to be worrying about it. The CAN protocol, the protocol itself using a polynomial method, it is going to calculate 15 bits of the data. A sequence gets generated depending on the data you are transmitting. So whatever data you are transmitting, depending on the CRC sequence will be calculated and it will be sent. So what does the receiver do is, the receiver after receiving the data, it will also get a CRC sequence generated and then it compares with the CRC sequence what has been transmitted. Okay, and depending on that, you are going to confirm whether you have received the proper data or not. Okay, so depending on the data you're going to transmit, CAN is going to generate a CRC sequence, and depending on the data what has been received by the receiver also gets a CRC sequence generated. When both the CRC sequence matches, it is understood that the data has been transmitted and received properly. Else, it is understood that the data transmission and reception has gone somewhere wrong. Okay, and CRC delimiter is a single recessive bit. So that is about the CRC field. Then the next field is the acknowledgement field. Let's go there. Next field is the acknowledgement field. It just consists of two bits. The first bit is the acknowledgement bit. The second bit is the ACK delimiter. So remember, delimiter again is a recessive bit, means it is always 1. For example, if somebody wants the acknowledgement, it is being given by this bit. So this bit is set to recessive by the transmitter generally, but will be set to dominant if the receiver acknowledges the data frame. So what happened in case of I2C protocol? Whenever I am transmitting, the transmitter used to pull the line up and the receiver used to pull the line low to give the acknowledgement. Okay. So similarly, in the CAN protocol also, whoever has been transmitting, the transmitter will make this bit 1. Okay, recessive means the transmitter is going to make this bit 1. After the data has been received by the receiver, he is going to make the same bit a 0. So that is how an acknowledgement is been given, saying that I received the data. Okay, so same as that of I2C protocol, the wired and concept. So here also, the one who's going to transmit is going to pull the line up, which means you make that bit as 1. The one who's going to receive is pulling the line low, means you are making it a 0, indicating it as an acknowledgement. So that is something with respect to the acknowledgement field. Then coming to the last field, um, it is nothing but the error field, end of the frame field. Okay, so the last is the end of the frame field. Understood all the fields? Understood all the fields? So we have got 7 fields. Is this been clear with all the fields? Arbitration field, control field, data field, a CRC field, acknowledgement field, and end of the frame field. Is this been clear? Okay. So let's get back to the types of the frames. So we have got 4 frames. One is the data frame. You can see here. First, in case of data frame, it is the SOF, which stands for start of the frame. Then is the arbitration field, then control field, then data field, then cyclic redundancy check field, then acknowledgement field, and end of the frame field. So remember, this end of the frame field is 7 recessive bits. Okay, you can see all of them has been high itself. So 7 recessive means 7 ones. Okay, end of the frame has been sent by using 7 recessive bits. So that is about the data frame. It is having all the fields in this. Now remote frame is very similar to this. Can you tell me which field in the remote frame is absent? Out of these out of these fields, which field do you think will be absent in the remote frame? Remember, remote frame is being transmitted to receive the data. Okay, it is to receive the data. Which one do you think will be absent in the remote frame? Come on, out of these fields, which field will be absent in the remote frame? So in the remote frame, I said I'm going to read the data. Should I be transmitting the data? Should I be transmitting the data in the remote frame? If I have to read the data, Should I be transmitting the data? Why should I be transmitting the data if I have to read? I want to read it from some other node. Why should I be transmitting the data? No, right? So only data field is absent. Okay, only data field is absent. You see, SOF is there, arbitration field is there, control field is there, CRC field is there, ACK field is there, and EOF field is there. So what is the one major difference? One thing is data field is absent. Second thing is the RTR in the arbitration field has to be 1 this time because you are going to read the data. The RTR in the arbitration field has to be 1. So that is the only difference with respect to the data frame. So remote frame and data frame are similar to each other. In case of remote frame, data field will be absent, RTR will be 1. In case of data frame, data field will be there and RTR will be a 0 because you're going to write. So data frame and remote frame are similar to each other. Okay, this is why I said if you understand data frame, remote frame comes by itself. Okay. Next. So once fields are understood, frames are very easy. The next we have got is the error frame. Okay, next important frame is the error frame. So remember, in case of error frame, this is the frame which is being transmitted when there is an error happening. Okay, so whenever there is an error, it is going to have an error frame transmitted. So it is having two things. One is the error flag, the other one is the error delimiter. So error delimiter is being fixed. It is 8 recessive ones. You can see here, error delimiter is fixed. It is consisting of 8 recessive ones. Okay. But coming to the error flag, it is calculated depending on the state of the device or state of the node. Okay. It is calculated depending on the state of the node. So usually a node will be in any of the 3 states. You have got active state, you have got passive state, and there is another state called as the bus off state. Any node you take will be in either of these 3 states. So it will be either in the active state, passive state, or the bus off state. So if a device is in the bus off state, that means there is no use of that node. Okay, so bus off state means it is to indicate that there is no use of that particular node. So the other two states are active state and passive state. So if the node is in active state, error flag will be 6 consecutive dominant bits, means 6 zeros. Okay, so error flag will be 6 zeros if the node is in active state, and error flag will be 6 ones if the node is in the passive state. Okay, in bus off state, there is no reason for generating an error flag. So it is out of the concept. Okay, bus off state means the node itself is not alive. So error doesn't get generated if the device is in bus off state. So if the device is in active state, you will have 6 zeros generated as an error flag. If the device is in the passive state, you will have 6 ones generated at the error flag. Okay, so that is about the error frame. So you have got two fields. One is error flag, the other one is error delimiter. It is 8 ones. Error delimiter is 8 ones. Error flag is depending on the nodes being active or passive. So that is about the error frame which gets transmitted if there is any error occurring in the node. Okay, so whenever an error happens, an error frame gets transmitted in the data bus. Every node will see that error frame and understand that there is some error happening in the transmission. So they will think that maybe the device has to retransmit, or maybe the other nodes have got the chance to stop the communication. Okay, so that is about the error frame. Then coming to the last frame is the overload frame. So whenever you want to transmit data frames or remote frames one after the other, and you want gap in between, you want some time to be wasted in between, so that there is some time gap given between the two data frames or between the two remote frames. So you are going to transmit a overload frame. Okay, so you can be transmitting a overload frame just to create a delay between the successive transmissions or successive receptions. So you can transmit a overload frame. So this has got two things. One is overload flag, the other one is overload delimiter. So overload flag again is let's say it is fixed. Actually both of them are fixed. Overload flag consists of 6 dominant bit. Overload delimiter consists of 8 recessive bits. So 6 dominant means 6 zeros, 8 recessive means 8 ones. Okay, so overload frame is fixed. Whenever you want to waste some time in between the data frames or the remote frames, you can transmit an overload frame. Its data is fixed. So overload flag has got 6 dominant bits and overload delimiter has 8 recessive bits. So these are the 4 frames of the CAN protocol: data frame, remote frame, error frame, and overload frame. Understood these? Everybody, is this been clear? Understood the 4 types of frames? This is important, guys. It is not that I'm just giving you an idea. It is important. Is this been clear? Okay, so we discussed all the fields. I hope you people are clear with that as well. Last 2 slides. So please pay attention. Last 2 slides. I just have got another 5 minutes to finish. So error handling. What are the types of error you might come across? Is this. Okay, this is nothing but error handling. So first one, if you can see, is the error detection. What are the errors can be detected? This is the error signaling. How is the error being signaled? Okay, so whatever it gets whatever error comes, there will be an error frame which is getting generated. Remember, so everyone is going to receive the error frame and understand that somebody is getting the error. Let's stop the transmission, or after some time there are chances of using the bus for the other communication, other nodes to communicate. Okay, so let's say what is a bit error? So bit error happens in the wired and CAN concept itself. So whatever is being transmitted, I should be able to see it back. So usually in CAN protocol, if I'm transmitting a 0, I should see that there is a 0 getting transmitted. If I'm transmitting a 1, I have to see that I'm transmitting a 1. So if I see different bits, if I'm transmitting a 0 and I am getting a 1, then that indicates the bit error. So whatever is being transmitted has to be received. So if you are not receiving whatever is being transmitted, then that creates a bit error. So that is the first type of error. The second type of error is the stuff error. So we have got another type of error, and usually the CAN protocol follows something called as the stuffing rule. So the CAN protocol always follows something called as the stuffing rule. So whenever you have to be transmitting consecutive bits, that cannot happen in the CAN protocol. So let's say I want to transmit consecutive 6 zeros. Okay. So can you people just remember and tell me where have we used 6 consecutive zeros so far? So where have we been using 6 consecutive zeros or 6 consecutive ones? So yes, if you remember, we have been using it in the error frame. So if the device has been in the active state or it is in the passive state, So depending on that, the error flag will be created. It will be 6 consecutive zeros or 6 consecutive ones. So let's say I want to transmit a data which is of 6 consecutive zeros or 6 consecutive ones. So that is not possible to be transmitted, because let's say I transmit 6 consecutive zeros, the other nodes will see it as some error. Okay, other nodes, there are chances of seeing it as an error. So because of that, I cannot be transmitting the consecutive bits like this. So if I have to do so, I have an option called as the stuffing rule. So there is something called as the stuff rule which has to be followed. If I want 6 consecutive bits to be transmitted, first you have to transmit 5 consecutive bits, then change the polarity, then transmit the sixth bit. So for example, if I want to transmit 6 zeros, transmit 5 zeros, change the polarity, then transmit the sixth bit. So again here, if it is 6 ones I want to transmit, so transmit 5 bits, 1, 2, 3, 4, 5, then change the polarity, which is 0, then transmit 1. Okay, so you have to make sure stuffing rule is being followed. This is the stuff rule, this is the other stuff rule. So you have to be following the stuff rule. If this is not being followed, it generates a stuff error. Okay, so it is going to generate the stuff error. Guys, remember, it is not going to tell this is the error. So it can never identify the error. It just generates an error frame. So there are chances of these errors being detected. Okay, so bit error can be detected, stuff error can be detected. It is not going to tell this is the particular error. It generally generates an error frame and gets it transmitted. So that is about the error detection. Coming to the error signaling. So CRC sequence, if it is not a match, I said transmitter transmits the data and transmitter will have a CRC sequence generated. Receiver receives the data and receiver will also have a CRC sequence generated. If the two sequences doesn't match, then there is a CRC error generated. Why we use this stuff error? So as I said, there are chances of this data being misconcepted as the error, as a error frame. Okay, so you have to make sure that means you just get an error generated, an error frame gets generated, but you have no idea of why is the error getting generated. That is when you have to check if I have followed the stuffing rule or not. So even if the stuffing rule has not been followed, you get the error generated. That is what I meant. Okay, fine. So CRC error gets generated. Then there is form error. So means the fields of the frame has to be properly arranged. Okay, so one after the other according to what the frame format is. The form error has to be sorry. The frames have to be formed. If the frames are having some illegal bits in between, it is going to have a form error generated. Then coming to the acknowledgement error, let's say somebody is expecting an acknowledgement and you're not giving the acknowledgement. So that also causes an error. That is the acknowledgement error. So these are the errors which can get arised when the transmission or reception is happening with the CAN protocol. So it just generally generates a error frame using which you have to yourself identify which are the errors which might have got caused. Okay, so these are the errors which can happen during the CAN protocol, transmission or reception in the CAN protocol. Is this been clear? Understood? Okay. So last slide, I said that here in the error frame, I said depending on the devices being in the active state or the passive state or in the bus off state, I said error flag gets generated. But how is that a device going to the active state? How is that a device you're considering it as an active state or passive state or the bus off state? Okay, usually in case of transmitter, there will be something called as transmit error counter, okay, which we generally call it as TEC. Every transmitter will have transmit error counter. Every receiver will have receive error counter. Okay, every transmitter will have transmit error counter. Every receiver will have receive error counter. So what generally happens is, whenever there is an error happening, let's say transmitter is telling I have transmitted the data, but let's say receiver is saying I didn't receive it, then that is an error to both of the transmitter and the receiver. Or let's say there is some particular error which is happening only with respect to the transmitter, or some error which is happening only with respect to the receiver. Every time an error is happening with respect to the devices or with respect to the nodes, this error counter is having the count of it. The number of errors count will be kept using the transmitter error counter and receiver error counter. Okay. Now, whenever the transmit error counter or receive error counter lies between this range, okay, so if it lies between 127, if it is greater than 100 and, I'm sorry, if it is greater than 255, then it is the bus off state. So if it is lesser than 127 and it is okay, it is lesser than 127, it is the passive state. Greater than 128, it is the error state. I think I said it in reverse. So if it is TEC greater than 127, okay, if it is greater than 127, it is the passive state. Okay, I said it in reverse. So if this TEC or REC, okay, the transmit error counter and receive error counter, if it is greater than 127, then it is considered to be in the passive state. So if it is lesser than 128, okay, if it is if this TEC or REC is lesser than 128, from 128 to 255, so that belongs to the active state, and the greater than 255 belongs to the bus off state. Okay, so depending on this value, you are going to consider or you are going to get the error flag generated. Okay, if it is greater than 127, it is the passive state. If it is lesser than 128, it is the active state. And if it is greater than 255, it is the bus off state. And whenever error gets generated, the counter will increase. And if the error has been resolved, counter value also gets decreased. Okay, so error occurs, counter increases, error is resolved, counter decreases. So if it is greater than 127, I'm repeating again, it is in the passive state. Lesser than 128, it is the active state. Then it is the bus off state. So when TEC is greater than 255, it is the bus off state. So bus off state in the sense, it is treated that the device is no longer eligible to be present in the network. So it treats it as a waste node and usually it will be removed. Now, if the device is in bus off state and it wants to come back to the active state, it is possible only to be brought back to the active state. So if the device is in the bus off state and you want to bring it back to the active state, you have to either reset the CAN controller or you can transmit 11 consecutive recessive bits for 128 times. So 11 ones have to be transmitted for 128 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Like this, 11 ones have to be transmitted for 128 times. That is when a device from the bus off state can be brought to the active state. So else you have to reset the CAN controller. So this is how you judge whether the device is in the active state or in the passive state or in the bus off state. Understood this? People, are you clear with this? Okay. So that is it about the CAN protocol. So you saw how to transmit the data using twisted wire cable. You saw different types of frames, different types of frame formats. There's standard frame, there's extended frame. You saw different types of frames, that is data frame, the remote frame, error frame, and the overload frame. And then you saw the fields present in each of the frame and how to decide whether the node is in the active state or in the passive state or is in the bus off state. So that is about the CAN protocol. So we don't have the CAN compatibility in our microcontroller, as I showed you in the very basic example, that our microcontroller has got a CAN controller for short, but CAN transceiver has to be added externally. So we don't have it. So we don't have a project to show you how the communication is happening using the CAN protocol. But I hope you got a fair idea of how is that actually working and how is the frames are being generated and how the frames are being transmitted. So that is about the CAN protocol, and that is it. Your module is done. Any doubts? No. As I said, we don't have any codes related to the CAN protocol. So it is sufficient to know it theoretically. So later, if you get any CAN transceiver in between, you can make use of it. Relays. Okay, so because it is already time, let me get back to it when I'll be explaining the project. Okay, so I don't think it is really required right now. I'll be talking about it when I go with the project. But basically, you ping me what and all information you need related, or if you want something in brief, I can do that as well. Let me know what you actually require for that so that I can have things prepared and then let you know. Now it is already time anyways. I'll not be able to take that up. Okay. So whatever is required, you can ping me up in WhatsApp personally, or I'll have it done for sure. Okay. Microcontroller slide PDF is not in Moodle. Okay. So in that case, I'll ask ma'am to add. Okay. Today's attendance is already marked. How is that even possible? Did you people mark the attendance by yourself? No? Okay. Then please use this code and have your attendance marked. Please mark your attendance. That is it. Please mark your attendance, and once you are done marking the attendance, you can quit the session. That is it. You don't have class tomorrow, and we will be meeting on Monday. I'll be giving you the fair idea of project actually on Monday. I'll be explaining you the requirements, and if time permits, I'll also be starting with the code along session. Okay, so that is how things goes. So we'll start with a project on Monday. So please make sure you finish your pending tasks before Monday. Okay, because once coding starts, you have to make sure that you concentrate on coding. So please make sure you are attending the class on not Monday. I'm very sorry. It is on Tuesday. So we'll start the project on Tuesday. Monday is a holiday. So we'll be starting on Tuesday. I'll be taking the code along session on the same day if time permits. Okay. So that is it. Thanks for attending the session. We'll meet on Monday. Thank you all. It is showing the date twice. Please wait. Let me check. Please wait, guys. This I'll delete. Okay. So you must be able to mark attendance now. Yes, I see few of you are marking it. So please mark the attendance according to this. No, there is only one project in MC. Guys, please mark the attendance according to this. There is only one session available now. Please be marking it according to this. And those who are done can quit the session. Somebody is giving me some doubts. Tell this also. On Monday, what is it? How does we are communicating via Teams? Explain according to the OSI layers. Okay, we'll see that. Alright guys, thanks for attending the session. I'll be waiting for 5 more minutes. Those who are done marking the attendance can quit the session. Thank you all.